In the high-stakes world of the modern operating room, a new era of surgery is unfolding. It is an era where the human hand, limited by fatigue and natural tremors, is augmented by a marvel of mechanical engineering, the surgical robot. Imagine a machine capable of operating on a beating heart or removing a microscopic tumor with the precision of a master watchmaker, yet with a strength that never wavers. These systems are not just tools, they are the most complex master-slave telemanipulators ever built by man. Hidden beneath their sleek white plastic carapaces are thousands of individual components working in a symphony of physics and software. We aren't talking about millimeters here, we are talking about microns. A single human hair is roughly 70 microns wide. These machines can consistently position a needle within a fraction of that distance. This is the story of how sand, rare earth metals, and advanced polymers are transformed into a life-saving titan of technology. This is the anatomy of the surgical robot.
The journey begins with the chassis and the mechanical limbs. These aren't built from ordinary steel. Engineers utilize aerospace-grade aluminum and high-modulus carbon fiber to ensure the robot is incredibly light, yet exceptionally rigid. Why? Because even the slightest flex in the metal under pressure could result in a catastrophic error deep inside a patient's body. Each arm segment is precision machined using 5-axis CNC mills to tolerances of less than 10,000ths of an inch. Following the machining, the components undergo a multi-stage cleaning process to remove any microscopic burrs or industrial oils. They are then treated with a specialized medical-grade coating, often a matte finish, to prevent glare from intense operating room lights. These limbs must be capable of a range of motion that exceeds the human wrist, meaning the joints must be designed with complex internal channels for wiring and cabling, all while maintaining structural integrity. Every gram of weight saved or added is calculated to ensure the motors can respond with zero latency and absolute stability. How does a robot move with such fluid, jitter-free precision? The secret lies in the gearbox, specifically the harmonic drive. Standard gears have backlash, a tiny gap between teeth that causes a wobble. In surgery, backlash is unacceptable. A harmonic drive uses a flexible spline and an elliptical wave generator to create a massive gear reduction in a tiny space with zero backlash. As the motor spins at high speeds, the harmonic drive translates that into slow, incredibly powerful, and perfectly smooth movement. These components are manufactured with such precision that the teeth are measured in microns. To ensure they last for thousands of surgeries, they are lubricated with synthetic, high-performance greases that won't degrade or leak. Every time the surgeon moves their hand an inch at the console, these gears work in unison to move the robot's tip a mere millimeter, a process known as motion scaling. It is this mechanical conversion that allows a surgeon to stitch together blood vessels thinner than a thread of silk without a single tremor. Deep inside the robotic arms, movement is transmitted not by heavy shafts, but by a network of high-strength cables, the tendons of the machine. These are often made from tungsten or proprietary stainless steel alloys, woven into ultra-thin strands for maximum flexibility and zero stretch. Each cable must withstand hundreds of pounds of tension without elongating even a fraction of a percent. They are routed through a series of micro-pulleys and fairleads designed to minimize friction. If a cable were to stretch or fray, the robot would lose its micron-level accuracy. To prevent this, sensors continuously monitor the tension in every line. The assembly of these cable systems is one of the most labor-intensive parts of the build, requiring technicians to hand-string the cables through the joints, much like stringing a high-tech instrument. These tendons allow the wrist of the robot to rotate 720 degrees, far beyond the capability of any human surgeon, allowing for angles of entry that were once thought impossible. For a robot to be safe, it must feel its environment. This is achieved through a sophisticated nervous system of force-torque sensors and encoders. Nestled at the base of each motor are optical encoders that track position thousands of times per second. They use light and etched glass discs to tell the computer exactly where the arm is in three-dimensional space. Furthermore, advanced surgical robots are now being equipped with haptic feedback sensors. These strain gauges are etched directly onto the metal components of the surgical instruments. They detect the resistance of tissue, the pull of a suture, or the hardness of a bone, and transmit that data back to the surgeon's fingers at the console. This requires a massive amount of data processing. Every movement generates a stream of digital information that must be processed in less than 10 milliseconds to avoid lag. If the surgeon feels a delay, the illusion of being inside the patient is broken.
This is the marriage of silicon and steel, ensuring the machine and the human are in perfect sync.
A surgeon cannot operate on what they cannot see. The robot's eyes are a high-definition, three-dimensional endoscope. Unlike a standard camera, this device contains two separate optical channels, mimicking human binocular vision. At the tip of this long, slender tube are two high-resolution CMOS sensors, often smaller than a grain of rice. These sensors must withstand the brutal heat and pressure of an autoclave, the machine used to sterilize equipment at over 270 degrees Fahrenheit. Surrounding the lenses are fiber-optic bundles that deliver intense, cool light into the dark recesses of the human body. The image is processed by a dedicated video tower, which aligns the two views to create a perfect 3D image for the surgeon. This vision cart also uses algorithms to sharpen the image, remove the noise of smoke from cauterization, and even overlay digital maps of the patient's anatomy using pre-operative CT scans. It is a level of clarity that exceeds the naked eye, magnified up to 10 times. The console is where the human and machine become one. This is the master in the master-slave relationship. Here, the surgeon sits in an ergonomic cockpit, looking into a high-resolution 3D viewer. Instead of traditional surgical tools, they use master controllers, specialized handles that capture every nuance of their hand movement. These controllers utilize magnetic induction sensors to track position without any physical contact, further reducing friction and increasing longevity. As the surgeon's fingers move, the computer interprets the intent. It filters out the natural 6 to 10 Hz tremor present in all human hands, leaving only the intended path of the instrument. The console also features foot pedals that control secondary functions like cauterization, camera zooming, and instrument switching. It is an immersive environment designed to reduce surgeon fatigue during procedures that can last upwards of 8 hours. The relationship between the console and the robot arm is governed by millions of lines of code, a digital bridge across a physical gap. At the business end of the robot are the end effectors, the tiny scissors, graspers, and needle drivers that actually touch the patient. These are masterpieces of micro-manufacturing. Some are so small they can fit through a hole the size of a pencil eraser. Each instrument has its own miniature cable drive system and wrist that provides 7 degrees of freedom. The manufacturing of these tools involves laser welding, microelectrical discharge machining, EDM, and assembly under high-power microscopes. Because these tools are used to cut and cauterize, they must be made of specialized alloys like martensitic stainless steel, which can hold a razor-sharp edge while remaining resistant to corrosion. Many of these instruments are designed for a limited number of uses to ensure the mechanical joints never fail due to fatigue. Each tool has a built-in memory chip that tells the robot exactly what it is, how many times it's been used, and its specific calibration data. This is the sharp edge of engineering precision. Before a surgical robot ever enters an operating room, it must pass a gauntlet of tests that would destroy lesser machines. This is the quality control phase. Every individual joint is put through a burn-in process, moving continuously for hundreds of hours to ensure there are no manufacturing defects in the motors or harmonic drives. Laser interferometers, tools that use light waves to measure distance, are used to verify that when the robot is told to move 10 microns, it moves exactly 10 microns. Engineers also perform electromagnetic interference tests to ensure the robot won't be affected by other equipment in the hospital, like MRI machines or cell phones. Then comes the torture test for software, simulating thousands of fault scenarios, such as power loss or sensor failure, to ensure the robot always fails into a safe, locked position. Only after surviving months of rigorous validation is the machine cleared for its first procedure. There is zero room for good enough in surgical robotics. As the final panels are secured and the system is crated for shipping, we realize that the surgical robot is more than just a piece of hardware. It is the culmination of decades of progress in material science, computer science, and mechanical design. From the smelting of the aluminum to the etching of the silicon chips and the weaving of the tungsten tendons, every step is a testament to the pursuit of perfection. Today, these machines allow for faster recovery times, less pain, and better outcomes for millions of patients worldwide. But the engineering doesn't stop here. Future iterations aim for even smaller profiles, autonomous suturing, and the integration of artificial intelligence to assist the surgeon in real time. We are witnessing the dawn of the digital surgeon, where the boundary between the human mind and the mechanical arm disappears. In the realm of microns, engineering truly becomes a form of art, saving lives one precision movement at a time. This is how we build the future of medicine. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons.
If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.